Hello and welcome to Lecture 3 of Superposition and Interference of Waves in Phys 1201. This is the second lecture on standing waves. In this lecture we're going to look at some specific types of standing waves that can occur. We've already seen the wave machine vibrate in one mode. Here are two other modes. And this one, which is the longest we can make, is called the fundamental mode. The main point here is that there are many ways we can make the wave machine vibrate. I just used a few new words without really telling you what they mean, so let's take a moment to define them. First of all, a mode. So we have some object, and it's able to vibrate in a bunch of different ways. Each of those vibrations is a different standing wave. And we call all those possible vibrations modes. The fundamental mode, if you just find all of the possible modes, well, now find the one with the lowest frequency or the longest wavelength, same thing. That's the one we'll call the fundamental mode. The final definition is harder. Harmonic. Let's suppose we've found the fundamental mode. And let's suppose its frequency is something, F1, say. And some other mode that we've found has a frequency that happens to be n times the fundamental mode frequency. Then we call that mode the nth harmonic. Okay, is that all clear? Yeah, sure. No, probably not. So we're going to need to work through some examples before this terminology becomes anything like clear. My suggestion is that you keep these particular terms in mind and watch out for them throughout these examples and keep coming back and see if you now understand them. We can learn a lot about the modes on an object just by drawing them following some simple rules. So let's think of this wave machine or some other system with free ends. And the rule is that free ends have to be antinodes. So I'm going to draw for myself that I have to have antinodes here. And I'm going to try and draw the longest possible wave I can. And we've actually seen it. The longest one has one node in the middle. We can't make a longer wave than that. So here is the standing wave. And this is the longest one that's possible. So this is the fundamental mode. And I want you to notice that if we trace this out, and then, of course, the wave stops here, but let's extrapolate there. You see that the wavelength crest to crest is all the way out to here. And so the wavelength is 2 times the length of the system. You could also see that by remembering that the distance between antinodes is half of the wavelength. And we've got antinodes that are L apart, and so L is half the wavelength. Well, let's draw the next longest one. So again, we have to have antinodes at the ends. And the way to make the next longest one is going to be to insert another antinode in between. And so there will be nodes halfway in between those, and the wave will look like this. And again, you can use that rule that the distance between antinodes is half of lambda to see that there's half of a lambda, 2 halves of a lambda, crammed into the length here, and so the wavelength is L. One more. So again, we have to have antinodes at the ends. I'm going to insert another antinode, so we need 2 antinodes in here. So making the antinodes evenly spaced. This is getting a little harder to draw, but I'll give it a shot. There, I think I've got them about equally spaced. Put the nodes in between and draw through all of these. And again, you can count half wavelengths, antinode to antinode, half a wavelength, 2 halves, 3 halves. So we have 3 halves of a wavelength in L. Or in other words, the wavelength is 2/3 of L, or 2L over 3. There's a pattern we can spot here. It requires doing some things that look a little weird at first. Here's the wavelength of our fundamental mode. I'm just going to call it lambda 1. Notice that going from this lambda to this lambda with the next longest mode, we've chopped the wavelength in half. Okay, so this is half of lambda 1. But one other way to write it that looks kind of silly but is valid is it is 2L over 2, right? That's the same as L. You might be wondering why the heck I would choose to write it that way. Well, I'm going to do something even stranger, and I'm going to back up and say, well, lambda 1 is 2L over 1. Now that seems totally pointless until you notice what's happening with our denominators here as we go to shorter and shorter modes. 2L over 1, 2L over 2, 2L over 3. Okay. So we can just keep going, and we can say there is some lambda that I'm going to call the nth one, and whatever n we choose, we'll be able to find it. It'll have a wavelength 2L over n. Those are all the wavelengths of the possible modes of this system. So let's now talk about this pattern a little farther and think about the frequencies. So here is our pattern of different lambdas, and all of them fit this mold. And we're going to now use the thing that we know is true of all sinusoidal waves, that v is f lambda. And this v for these waves will be the speed of sound. So that's a constant, which means for all of these we can say that the nth frequency is just v over the nth wavelength, which means we can now write these frequencies. F1, notice that is the frequency of the fundamental mode, is going to just be v, the speed of sound, over 2L. I could put the 1 up here. This F, I'm not going to label it yet, is v over 2L over 2. Well, okay, so that is 2v over 2L. Now that may seem silly, except I want you to notice that it is 2 times v over 2L, which is F1. So this is 2 times F1. But we've already said if a mode has a frequency that is n times the fundamental mode, then that is the nth harmonic. So this is F2. This mode is the second harmonic. We didn't actually know that until we verified that its frequency is twice the frequency of the fundamental. Similarly, if you do exactly the same thing, you'll see that this one is 3 times the fundamental, and so it is 3v over 2L. And this one will be the nth harmonic, nv over 2L, which is nF1. Here are various standing waves on bridges, and note that they can excite the bridge into various different modes. Here's a very famous example that led to the bridge collapsing. And one thing to notice about all of these is that the ends of these bridges are fixed in place. There are nodes at the ends. So those bridges that we just watched, and if you also watch videos of waves on ropes and strings, the ends are fixed. They're held in place, and so we get a different set of standing waves. Here's the longest, so this is the fundamental. And if you look at it, just as the distance between antinodes is lambda over 2, so is the distance between nodes, and so again we get that the wavelength here is twice the length. And again, you can make the higher harmonics by just inserting more nodes, and you see that the pattern turns out exactly as it did for an open-ended system. The remaining system to look at is one that has one fixed end and one free end. And again, we can draw the harmonics, the different modes, but now we will have to have a node at one end and an antinode at the other. So I'm going to draw several of these. Now look at this. This is a quarter of a wavelength, right? The distance from a node to the next node would be half a wavelength, and we're only getting halfway there because we're only getting to an antinode. And so we have here that L is a quarter of the wavelength, or in other words, the wavelength is 4L. And this is our fundamental. So again, using V equals F lambda, you can say that our fundamental mode frequency is the speed of sound over 4L. Now, something different from what we've seen happens here. This is 3/4 of a wave, right? There's a quarter, another quarter, another quarter. And so L is 3 lambda over 4, or in other words, this lambda is 4L over 3. Now look at that. That means this frequency is 3V over 4L. Wait a minute, that's 3 times the fundamental. So this is the third harmonic. What happened to the second? Well, it doesn't exist. So if you, and you can go through the same argument to see that this one is the fifth harmonic. And so we say that the only modes that this open-closed system has is the odd harmonics. The even harmonics are impossible here. The final example we're going to look at, because it's very common, is standing waves in pipes, like flutes, organs, clarinets, whatever, but it could also be pipes in industry, great big boreholes, any tube full of a liquid or gas. And these are standing sound waves. So before we look at them, we should take a moment to understand the nature of sound waves a little better. We can't see them. It's hard to visualize sound waves. This simulation from the Physics Education Technology Group at the University of Colorado is about the best visualization I know of. And if you watch these sound waves propagate out, you see them travel, and there are compressions of the air. In contrast, though, if you watch one air molecule, and they've helpfully put these X's on some of them so you can watch them more easily, it vibrates back and forth, and notice that it vibrates parallel to the direction of propagation of the wave. And so sound waves are longitudinal. So just like a wave in any other medium, when a wave gets to the end of a pipe that it's propagating along, it reflects back. And so now we have waves going in both directions, and it's possible to make standing sound waves inside the pipe. And these work just like any other standing wave. The main thing is that you need to know how the ends work, how the boundary conditions work. So if an end of the pipe is open to the air, air molecules are free to move back and forth there. There's nothing holding them in place. Now this happens often. For example, in a flute, the hole that you blow over at one end is open to the air, and whatever the first open finger hole is would be the other open end. And so like any other free end, these places will be antinodes. You see the same thing in things like organ pipes. There are these slits down here that are open ends, and the top ends are open as well. In contrast, when you have a closed pipe end, the air molecules are basically stuck against the wall. They can't move, they're fixed. So in a clarinet, for example, while the first open finger hole would be an open end, sort of surprisingly, the end you blow into is closed. There's a reed that mostly blocks the end, and it behaves as a closed end. And so, like any place where things are fixed, this will be a node.